I want to say a couple words in response to you, Ernie. You know, you are my test bed, the Grandma Just button. Like, I mean, when I first met him, he's like, why? And he, honestly, that 17 hours that we spent really pushed my knowledge and my understanding of it to come into new ways to explain it, which has helped me relate to people a lot more in the tech. Remember the first interview? You're like, well, I don't understand this. What are you, some alien, whatever. Remember that? As we got to know you, so Ernie's, he's been a big part of it as well, man. He's one of my good friends. Like, he's been fighting this fight since 1996. 88. That is some fucking dedication. Seriously, a round of applause for this guy. He never, ever gives up. And Donna, his wife. Yeah. I mean, she's the woman behind the scenes, man. I mean, that's the only thing that I found. You know, the only failure you ever experience in life is when you give up. So if we keep on keeping on and keep going, we will get there. And people like this are an inspiration for that. He has taken shit his whole life. He's that libertarian, but he's still going.
Bring it. Thank you, Colin.
Much love, brother. All right, so I usually make my presentations like half an hour before the show, sorry. And they started half an hour early. So I wanted to water it down and make it a little bit less technical, so I might skip some slides. Feel free to tell me to slow down if I'm talking too fast. There's a lot of content here, so this specific one is an unstoppable internet protocol. But it's TCP/IP, if you guys are familiar with it. That's the common protocol that most of the internet runs on. It didn't really gain adoption in the 80s until it was actually embedded in the BSD Unix kernel, right? So embedding a network stack in a kernel helps with the adoption of it. But more precisely, one reason that we are developing this is because just through my journey of understanding Bitcoin, understanding computers, understanding software, reading code, I ran into a lot of issues and architectural issues, and I started noticing that everything's kind of built on this inverse foundation. You got this little foundation of sand, and then everything's built out on top of it. Kind of, it's a little lopsided and unstable, and then people keep building on it because they think that that's innovation. More code is better, but that's not necessarily true. It's actually, if you can get the same functionality with less code, you're a better coder. So through that whole process, it kind of metastasized into an operating system and a new routing protocol. So if you guys are familiar, you have what's called an IP address. IP stands for Internet Protocol. It's just, in a simple sense, it's just a number that a computer can read that maps to a physical location, right? But the IP address acts as an identifier and a locator. So one of the big distinctions with the one stack, okay, is it separates these types of things. So think about it. When you are on your computer, you're on the Wi-Fi here, you got an IP address. You go home, you got another IP address. So if you're trying to have a peer-to-peer communication, how do you know where your peer is and what IP address they're on, right? It's always changing. So imagine if, like your phone, where you roam between different networks, that IP address won't change. So you have a static identifier and the locator goes underneath that. So this specific presentation is basically focused around security-focused operating system design through the one stack. So you guys have a reference. The internet, as we know it, developed a reference model, I believe, in the 1970s. ARPANET was, I think, 1969 was RFC number 1. 5-bit message address, just 40 different nodes on the network, and then it grew into the internet as we know it. But it runs on a reference model called the OSI, which stands for Open Systems Interconnection. So that stack is completely unauthenticated through my understanding of network security. I gained a lot of this understanding by having mentors. The IETF, as Ernie says, what does that mean? Internet Engineering Task Force. So that's where the internet's built. That's where all the RFCs are standardized. That's where everything that everybody uses comes from, right? So I spent a lot of time developing this architecture since about 2015, 2016. And, it's not really yours until you put it into the fire, right? You can have a good idea, but you don't know how good it is until you get some peer review. So I took it to the IETF quite a bit and had all the old dogs in the wolf den try to rip it apart. And I started walking away unscathed. And I was like, okay, I think I'm onto something. And that was just simply in the consensus layer. So I'm going to skip maybe a little bit some of the techie stuff, but I really want to also hone in on the economics, right? That's one of the fundamental things. We have an issue with the internet. For one, it's unauthenticated. So if you're on this Wi-Fi right now, right, I can actually send out a packet called an ARP packet and poison your cache, and I can make all your packets go through me, and then I can see what you're doing, even if you have SSL, because I can just strip your SSL off, and whoop, there's your passwords, right? Because ARP messages are not authenticated. So even the packets that you source from, not authenticated. You have no way to verify that somebody is somebody. Even an email, you get those spam emails. It's because there's just a simple little text, it's called reply to, in the email header, and that's what says to reply back, and that's what you see on your email client where it says this is from who. So you can spoof that, you can spoof IP addresses, you can spoof even telephone numbers, right? So everything we have today is really completely unauthenticated. And then the software, even on the operating system in itself, is unauthenticated. That's how you get viruses and worms that can inject themselves in the file system. It doesn't really know itself. So the ultimate design goals of this is to create an open protocol that anybody can join, anybody can be a part of, but shifting the economics from a type of system where you pay into it for a membership, such as I pay my ISP and I pay for the hardware, to where your hardware actually becomes a form of monetization. And that's one of the big missing gaps that I think the world has missed in getting these 5 billion other people connected to the internet. Facebook has tried it, Google has tried it. They've all failed because they're trying to do it in a centralized way. Sarnoff's law, which is just a linear relationship. What we're really trying to capture is Metcalfe's law, which is V equals N squared, which the value of a telecommunication system is proportional to the square of the participants. In other words, we multiply value exponentially, right? So if you look at all the richest people in the world, Carlos Slim, all of them, telecommunications monopolies. Bell, right? Telecommunications monopoly. They're some of the most lucrative businesses because of the exponential proliferation of value. So we need to put that into people's hands and take that exponential value, and instead of it going to a central form, it can go to all of us and become a distributed system, right? And then that also creates an economic value in places that are deprived because of borders and currencies. And that's the biggest fundamental issue of why people aren't connected to the internet, is because there's no money to be made there, right? It's $100 a month for Starlink. Who in Africa is going to pay for that? They don't have money, right? That's the problem. So if we solve that economic issue, then we solve the connection issue, and then Metcalfe's law, about 2 billion people connected online right now. Imagine the value at 7 billion instead of 2 billion, right? Let's say we're doing it exponentially by the square, 4 versus 49. Tell me what one's higher. So a lot of people have tried to solve this issue, right, because of this exponential value increase, but it just they haven't been able to see the economic issues. So this whole thing is wrapped up in an operating system called LXOS, and the network model is built on this called the one stack. So it's Open Nexus Execution Stack. Okay. So it's a stack designed to replace this OSI reference model, but it's a fundamental reference for the Nexus protocol. So instead of having an IP address, you're going to have an NP identifier, right? So Nexus protocol is its own independent routing system. And a lot of people here talk about mesh networks, right? Mesh networks don't work because IP addresses, you can get static mesh networks to work, but if you have a dynamic mobile mesh network, you're not going to be able to re-upload IP addresses to different routers every time you move locations, right? And you have an RF saturation issue, which means if you look at a light bulb, that's isotropic radiation, right? It's spreading out in a sphere, okay? That's what RF frequencies generally do, especially with Wi-Fi. They're not highly directional. What we're doing is using laser beams so that you get this really high directional gain and you don't get as much RF saturation of the airwaves, because the airwaves can only carry so much RF. So when you're talking about high population density areas like New York City, if you've ever been to a really big concert, your phone doesn't work. Why? RF saturation, because all your phones are running low gain and there's isotropic radiation saturating the airwaves, loading up the towers, and nothing works, right? So mesh networks really break down in high population densities. The concept is there, but the technology hasn't. And seeing that gap, that's part of what has driven this innovation to develop the Nexus protocol and LXOS. So the one reference model right here, this is broken up into 2 sets. Right here, this is the Tritium software stack. So this is existing, it's running right now. This is what powers Nexus, right? Network here, as you see, it connects in, and we break the network layer into 5 sub-layers, and then we take on the one stack, on this side, the consensus layer becomes part of this blockchain, right? This is the ledger register operation layer. This is our whole smart contract functionality. The reason we did a stack-based virtual machine is because stacks work, they're fast, and you have a different defined role for each specific layer. So the ledger only processes cryptographic data, the register verifies pre-states and post-states, and the operations mutate or change the values of specific registers. And then that's all driven by an API in the application space and logical and interface. So you as a developer generally live on the logical interface layers, right? So this right here, this is the goods of the one stack. This is just already existing stuff that sits on top. And one reason we have this consensus layer is it gives you a common reference point. One thing the internet does not have is a common reference point. So you rely on centralized authorities such as certificate authorities, for instance, where you have to buy an SSL certificate. The reason being is cryptography means nothing unless you have some sort of link into the real world. All it is a mathematical relationship between a public key and a private key and a signature. That's all it means. That's all it means. So you need to have some context for that public key. So if I create an SSL certificate that's self-signed, it could very well be me, man in the middle, attacking somebody here if you don't have that certificate authority to verify that public key, and you wouldn't know any different, right? So that's one way they protect against man in the middle attacks. It's still still doesn't protect against ARP poisoning and SSL strip, but it's a step towards that. But it still relies on central authorities, right? And those central authorities can deny SSL certificates, or they can grease backroom deals. The internet right now is regulated by ICANN. VeriSign controls .com, but there's already like grease and wheels going there where VeriSign can increase the cost of com however much they want. ICANN is supposed to be nonprofit, and ATF is supposed to be decentralized, but Google and Cisco kind of run it. It's supposed to be like decentralized working groups, but there's still a lot of politics and control there. So, a lot of this architecture has been developed through real world experience in the real fire, right? So this consensus layer is really fundamental because this gives us context without the need for central authorities. You can public keys for encryption. You can use all of that and reference that, but even more, you are able to tie a cryptographic identity to a network level identity. So you get this higher level of elevated trust on the internet where you can verify mathematically you are talking to the person you intend to talk to, right? And there's no way that they can spoof that specific identity. And that changes a lot of dynamics on the internet, especially we're in this time with the control of information. How many bots are on Twitter saying stuff? How do we know that? We don't. There's no way for us to verify that as people. And that's part of just a byproduct of the architectural issues of the current internet. That would not be possible because they would have to forward specific identities, and then you have a cryptographic verified ledger or associated data with that identity, which would generally follow a very simple algorithm, would be easy to detect, right? Because they would probably create one transaction, maybe create another. There's only so many combinations a bot can do. So we ain't gonna make it easy for them, right? So we go down below the consensus layer. This is the session of the transport layers. These are taken from the OSI. These are the only two layers that survived this design. The session layer is basically the sockets, SSL. Transport layer is UDP or TCP. So TCP, Transport Control Protocol. That is the one protocol that we're actually keeping from the existing internet. All it is essentially a reliability protocol. The internet scales because it drops packets, not because it forwards them. So you have to retransmit the packets a lot. If you want to have a consistent stream as a developer where you're reading the same bytes that were sent on the other side of the socket, you need to check, oh wait, did that packet get through? Oh, is this packet sequenced correctly? And you need to reassemble the binary stream. Sometimes a packet doesn't get through and you have to keep doing it. That's called a lossy Wi-Fi. And that's why sometimes you can see your connection get really, really slow, right? So TCP is really important. So this stack will run TCP NP instead of TCP IP. Then we get down to the identifier layer. This is what I was speaking about. This is where your actual digital identity lives, or the network level identifier. This is what people will be opening socket connections to. This is what your domain names will map to. It's a static identifier where the locator below this can change beneath, right? Now, a locator in this specific stack can be an IP address. So that's how we create interoperability, because this stack can sit, and then this locator layer and signal layer can basically be a subset of the OSI. So it acts as an ad hoc network as it's being proliferated. But over time, as more and more of the hardware gets put out, we rely less and less on IP locators from gateway nodes, right? The general other type of locators are going to be wide radius locators, geospatial locators. We'll get to that. Signal layer. This is essentially, it's called the signal layer because it's all wireless. So one of the big problems with designing a new hardware mesh is frequency licensing, right? You can't broadcast any frequency, otherwise you're a pirate radio station, right? Unlicensed broadcast, unlicensed frequency. You can't use ham radio unless you have our official license, right? So they control the signals. They control all of the frequencies, justifying it by radio frequency interference, right? Like a certain frequency can jam another frequency. So they regulate the shit out of the signals. So over time, that was always the biggest problem to crack. How do we solve the signal issue, right? How do we could get a constellation license, we could get a global license to the International Telecommunications Union, but how reliable is that going to be? They can pull the license when they want, and then that relies on some central company to own that license, and then sublease the license authority out to other people. So what I discovered through phase array antennas for high directional gain and other things is what's called an ISM. And this is somewhat of a hidden, it's not super well spoken about because it's pretty valuable if you're a hardware manufacturer that relies on sort of RF communication, because you don't need a license, period. But now ISMs they're not propagated, all the frequencies aren't accepted by all the countries. Different countries have different frequencies that they accept. But ISM was initially created for industrial, scientific, and medical applications. If you look at your microwave, it's always going to be 2.4 gigahertz. Why 2.4 gigahertz is an unlicensed ISM. So Bluetooth, 2.4 gigahertz. So every Bluetooth device that you have uses an unlicensed frequency. Now they regulate those frequencies. You have certain, FCC regulations, your broadcasting limits, and that was one of the challenges to figure out how to make a specific frequency work within their limitations, because their limitations are designed to make sure people like me can't figure out how to make communication systems without it. But we figured it out. We're using 5800 megahertz, 5.8 gigahertz. That's, if you see your Wi-Fi say 5 gigahertz Wi-Fi, it's that same frequency. It's actually not a very well used frequency. Everybody's using 2.4 gigahertz, and we don't have a limit on antenna gain. So what that means is gain is kind of like, you go from isotropic, the spherical, to a more focused beam, and higher gain is like a stronger laser. So as you get that higher beam, you don't get as much interference, but it also, you're not going to have people getting bombarded with RF, and it's more difficult to intercept your packets, right? So we get a lot of interesting security properties with that. We're basically, the maximum carrying capacity with 8 spatial streams of 5.8 gigahertz is 10 gigabits per second. That's 1.2 gigabytes per second just per 8 spatial streams. So it's got a significant amount of bandwidth. You need to have a low error ratio there, so you need to have really high signal strength because you're doing 1024-bit quadrature amplitude modulation. I'll spare you all the details. But essentially, we figured that out, which was a fundamental thing because the frequency licensing has to be free and open so anyone can deploy this hardware anywhere. 5.8 gigahertz is accepted in every single country in the world. Every Wi-Fi router supports 5.8 gigahertz. So they can't say anything when we're beaming 5.8 gigahertz to satellites, right? Because it's an unlicensed frequency. They can't stop it. Huh?
Range. What's the range?
500 kilometers at 44 dBi, 1024 quadrature amplitude modulation. That'll get you that 10 gigabits, 8 spatial streams. But generally, you'll probably get 30 dBi antenna gain, 500 kilometers. That'll be a little bit lower data saturation. Probably have to go to 512, 256 QAM, if you're familiar with QAM. You have to change the modulation, but I've designed it to be at about 500 kilometers inclination orbit, which is higher than your normal LEO, higher than the Kármán line, high enough to stay. A lot of people do 200 kilometers, 300 kilometers. We're designing it for 500 kilometers so we have a little bit of play. But the phased array antennas, if anybody doesn't know, is an electronically steerable antenna where you can actually, you use kind of like you dropping rocks in a pond. The ripples kind of can, if you drop the rocks in the right ways, those other outside ripples will push the inner ripple and shape it and form that beam. And so satellite dishes have to be moved to point, right? They get pretty decent gain, but they're still mechanical. Phased array antennas can switch at any point electrically, but another really important byproduct of phased array antennas is you have a lot of noise spill off around the phased array antenna. So if I'm trying to sniff your packets by pointing a radio at your phased array antenna, I'm just going to get noise. I have to be directly in your line of sight because you're using all these other frequencies to spill off and shape that beam to make it that laser beam to point up. So you actually get a really interesting security property, and you have a physical layer cutoff if anybody is bombarding you with packets. If you've heard of DDoS attacks, that generally happens because you're setting so many packets to the router can't drop the packets fast enough because the memory is not fast enough, the clock speed is not fast enough. Well, the only real remedy on that is to cut the physical link, but everything's just an open pipe and everything flows through it on the internet as it exists. This is electronically steerable. Oh, you're setting too many packets to me? I'm gonna point over there. Oh, problem solved, right? So the byproduct of this architecture solves a lot of issues that the current internet has. And so this is, like I said, it was born by speaking with people, like being mentored by some of the original fathers of the internet, like the first fellow of Cisco, Dino. He was one of my mentors. Other ones like Victor, Cisco guys, Google guys, Verizon guys, blah, 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 IETF. And I mean, I've exonerated and tested this architecture many, many times with engineers that I consider better than me, old dogs, to make sure I wasn't missing anything. And this is kind of the magnum opus of that.